Okay, so my name is Teruyuki Hirano. I'm gonna talk about algae jitters in m-dwarf today. So obviously, as Sarah mentions, young planets are a great target to understand the formation and evolution of exoplanets. They are a very important target to discuss orbital evolution or atmospheric evolutions. But as you know, there are serious technical issues, including to investigate those young planets, including stellar activity and rapid rotation. It is often said that the stellar activity is mitigated in the near infrared. Actually, this is partly true. For example, we investigated the photometric stellar variability by observing some m-dwarfs. Here we conducted multi-band photometric observations in the near infrared for some K2 m-dwarfs. Here we show the results of 4 m-dwarfs. And as a result of JHK band observations, we found that in all cases, for all m-dwarfs, the photometric variability amplitudes are suppressed in the near infrared by a factor of 2 or 3. And from this kind of observations, we can break the degeneracy between the spot filling factor and spot contrast. And from these observations, we found that spots are actually cooler than the photosphere, than the other photosphere by 200 to 300 Kelvin for those m-dwarfs, which was consistent with the trend that for cool stars, the spot temperature is slightly lower than the other photosphere. So stellar activity is actually mitigated in terms of the spot contrast. So we actually expected that also for our jitters, it should be mitigated in the near infrared. So we actually observed some very young m-dwarfs to discuss the stellar activity for young m-dwarfs. And this is the result for LB measurement by IRD, infrared Doppler instrument, which was introduced on Monday by Kotani-san. This is the result for LB measurement for K233, which is one of the youngest m-dwarfs known to hold transiting exoplanets. And the top panel shows the LB variations for achromatic LB, including YJH band. And the middle panel is the LB variation for the YJ band, and the bottom one is for the H band. So unexpectedly, the LB variation was actually more significant at longer wavelengths. So as I said, if the LV jitter is induced by only spot contrast, then we should expect a lower LV jitter for young m-dwarfs. But so this was actually something that we didn't expect. So we first suspected that this large LV variation in the H band is due to the Zeeman effect. Because the Zeeman effect, Zeeman line splitting, is basically proportional to the wavelengths as shown here. And according to some toy model, the LV variation due to the Zeeman effect is basically proportional to the square of the wavelengths. But we immediately noticed that the Zeeman effect alone cannot explain the large LV jitter in the H band. Here I show the lambda G factor as a function of wavelength. As you can see, the lambda G factor is much lower in the H band compared to the G factor in Y and J band. So the Zeeman effect cannot explain the large LV jitter in the H band. So we had again, we had a closer look at the m-dwarf spectra, the original spectra again, and try to understand what's going on. Here I show a comparison between 2 m-dwarf spectra. One is GJ436, whose effective temperature is similar to K233, the effective temperature. And the other one is GJ699, which is Barnard star. And the effective temperature of Barnard star is actually similar to the spot temperature on the surface of K233. And here you can see a significant difference, especially in the line depth ratio. Here in the Y band, where most of the lines are actually FEH lines. For cool stars, the lines are deeper. On the other hand, in the H band here, where most of the deep lines are OH lines, actually the lines are deeper for cool stars. Oh, sorry, lines are shallower for cool stars. So the reverse is true for H band. So we suspected this difference in the properties of line depth variation could be responsible for the large alpha jitter in the H band. So we actually implemented some analytic calculations to simulate alpha jitter. I know that there are several works trying to simulate the alpha jitter by some numerical simulations. But by numerical simulations, we sometimes lose some important information, such as what are the most important factor, or what are the key parameters to describe the alpha jitter. So we stick to the analytic calculation for the alpha jitter. Unfortunately, I don't have time to explain all the details of the analytic calculation, but basically we try to model the distorted line profile during distorted line profile due to the presence of spot, and try to derive the LV anomaly due to the presence of spot by calculating the velocity anomaly. And here's the result. Unfortunately, this is a kind of dirty equation, but if we can neglect the impact of the Zeeman effect and the convective blue shift, the alpha jitter equation gets something like this. Most importantly, the alpha jitter is proportional to 1 minus CR, where C is the continuum contrast ratio and R is the line depth ratio. I'll explain these parameters in the next couple of slides. The first one is the intensity contrast C, which is defined as the contrast ratio of the spectra for the photosphere and the spot. The C is defined like here. And for K233 like star with effective temperature of 3500 Kelvin, C is about 0.84 or 0.86 in the near infrared. It doesn't vary a lot in the near infrared between YJ and H band. But for R, line depth ratio, the situation is quite different. The R line depth ratio is defined as in this figure. So if the spot has a deeper line profile, then R should be higher than 1. But if the spot is shallower than the other photosphere, the absorption line, then R should be less than 1. And in the case of K233, the mean value of R was about 1.1 in the H band, in the Y band, but R was about 0.9 in the H band. And if we combine R with the continuum contrast C, 1 minus CR, which determines the magnitude of alpha jitter, was about 0.05 for the Y band, but it becomes 0.23 in the H band. So given these numbers, we can actually plot the alpha jitter for the case of K3. And here I show the alpha jitter as a function of the position of the spot on the stellar disk. Here, the X coordinate here in this figure is defined as in the on the right panel. The X-axis is perpendicular to the our line of sight and also the stellar spin axis. So as you can see, the alpha jitter amplitude is about 4 to 5 times larger in the H band than in the Y band. So the difference in the line depth ratio can at least partly explain the large alpha jitter observed for K233 in the H band. So what can we learn from this kind of this fact? Well, we can So basically, when large variations, LV jitter are observed for very active m-dwarfs, one should check for the line-by-line dependence of LV variations along with the other activity indicators such as BIS or FWHM. But I should stress that the chromatic index here defined as beta here is not always a good indicator because there's no guarantee that the LV variation is monotonically dependent on the wavelengths. And if the LV variation turns out to be originating from the spot modulation, then we probably have two directions to go. One is to try to find the set of spectral lines that are theoretically less affected by stellar activity. For example, CR close to 1 in the last equation. And the other, I know that there are some efforts trying to measure line-by-line LV to investigate activity. But if I understand correctly, line-by-line technique is only available, only work when you have a large number of LV data points, for example, 100 data points. But here I'm suggesting that analytic equation is very useful, even if the number of LV points is relatively small. The second option, B here, is more classical, which tries to find the indices, indicate some activity indicators and develop a method to decorrelate the LVs and the activity indicators. But as Sarah just mentioned in the previous talk, there are some warnings to apply some statistical method like GP, Gaussian process, to analyze the activity. And also, I'd like to mention about the more sophisticated technique introduced in yesterday's talks. Well, this is the last slide. This is the LV fit to K233. So we actually took the easier way to go. We didn't try to intensively analyze the activity indicator, but we just simply try to analyze the YJ band LVs for K233 and try to extract accurate information as accurately as possible. And this is the result. Unfortunately, the LV precision in the Y and J band is not so great, and we could place a very weak upper limit for the mass of the planet. But I would say this is a very accurate measurement for the mass of the K233. We got an upper limit of 31 Earth mass at the 95% confidence level. Okay, so this is the summary slide. And I just want to stress that the analytic model is sometimes useful to predict the line-by-line LV jitter and implement the analysis. Thank you for your attention.
Thank you for that really interesting presentation. Do we have any questions? I have a question, which is going back to the potential line-by-line analysis. Do you have any thoughts about, do we have enough information to estimate these contrast values for enough lines to do this in a line-by-line framework instead of a band-by-band framework?
Yeah, we can easily apply the line-by-line analysis because the parameter C or R can be estimated a line-by-line basis. So based on, but we need to assume some, theoretical models or something like that. But we can also use some observational data. For example, for this estimation, we use the theoretical model, but we can probably use some standard star m-dwarf spectra to estimate these parameters. And we can predict the expected LV jitter for line-by-line basis.
Okay, great. All right, well, if there are any other questions, let's thank Teruyuki again.